Welcome to Cassandra Lunch number 138. Don't forget to like and subscribe, as well as turn on the notification bell so that you can get notified every time we post a video or go live. Today, we will be discussing LLM fine-tuning with QLoRA, presented by Obioma, Anomnachi. And we will delve deeper into the world of large language models, fine-tuning, and in this session, the second in our series, we discuss the complexities and nuances of fine-tuning methodologies with a special focus on training a QLoRA adapter. The co-organizers for this event are Rahul and myself. If you are interested in being a co-organizer and want to help get speakers by reaching out to people in the Cassandra community around the world, drop me an email. My email is listed below. You can also reach out to us at the marketing email. If you are interested in giving a talk at Data Engineers Lunch, our sister lunch, you can reach out to me or the marketing email as well. We are part of a larger community called Data Community DC, which believes in building an inclusive environment. So no matter your race, gender, or sexual orientation, everyone is welcome, and we expect respect to be given to all. Data Community DC is actually made up of a lot of different groups, generally centered around data. You can find out more about all the various groups and events at datacommunitydc.org. What do we cover here at Cassandra Lunch? We cover all things that talk and play well with Cassandra. We cover open source Cassandra enterprise variants such as DataStack, Scylla, KeySpaces, Cosmos DB, and Yugabyte. We also talk tools in the ecosystem such as Spark, Kafka, and Airflow. If there's anybody new that you'd like to say hi, what brought you here, please do so. What you hope to get out of this, drop something in the chat. And don't forget to like and subscribe. A few rules. If you have a question, please ask it. Be polite and courteous to others and share what you know. Obi has said it's okay for me to interrupt him with an appropriate question in the moment. So please, please ask away and I'll get them to him. Here at Anant, we design, build, and manage global real-time data and analytics platforms surrounding Cassandra, Spark, and Kafka. So Cassandra is our bread and butter. Thanks to our sponsors, DataStax and George Washington University, among many other institutional and organizational sponsors. If anyone has any job offers or is looking for a job, please drop links in the chat. If anybody has any meetups, hackathons, classes, or conferences you would like to promote, please drop links to those as well. We host Cassandra Lunch on Thursdays at noon. And our sister lunch, Data Engineers Lunch, Mondays at noon. We have a third series, No Code Data and AI, which we host Wednesdays at 1 Eastern. All of our videos are available on YouTube, starting at Cassandra Lunch number 10 on the Cassandra Lunch playlist. We'd also like to highlight Cassandra.link, a great resource for getting information about Cassandra that's hand-curated by our team at Anant. And you can also learn more about Cassandra with our runbook series that you can find at anant.us/runbook. With that, I will pass to Obi. Obi, thank you so much for doing this, and I'm looking forward to the talk.
Yeah, thanks, Nick. Okay, so get started. As Nick said, my name is Obioma Anomnachi. I'm an engineer here at Anant. Today's topic is LLM fine-tuning with QLoRA. Specifically, what we're talking about today is the training process. We had a separate talk last week where we talked about our dataset generation. So just as a reminder from that talk, what we're doing here is instruction fine-tuning a QLoRA adapter for the Llama 7 million model. So we'll go over a little bit what all of those words mean. But specifically, the things that we're going to be talking about today are types of fine-tuning. This is actually a different sort of taxonomy of fine-tuning types than we did last time, where we talked about instruction fine-tuning or multitask transfer learning and things like that. This is a separate taxonomy that has to do with specifically the parameter efficient fine-tuning library provided by Hugging Face and how that relates to and differs from full fine-tuning methods. So just getting started with that. So first, just a quick reminder from last week, we're talking about transformers here. They're composed of attention blocks with positional encoding and feed forward layers, basically a big neural network. A reminder about what attention does is that it allows the sort of predictive model to take into account specific words and their positions relative in the previous text, rather than old NLP methods, things like Markov chains, that take into account just the previous word or the previous sequence of words all weighted equally. In this case, you can determine which words are important in order to determine what the next word is going to be. So fine-tuning methods we discussed last time are sort of about the composition of your data set. We talked about instruction fine-tuning, but there's also transfer learning, where you use a few examples. There is task-specific or domain-specific fine-tuning, but none of those have to do with what you're doing with the actual neural network that is your model. What they really have to do with is what your data set looks like. But this time, what we're talking about is how does your fine-tuning method affect the actual neural network that you're working with? So in this case, the first thing to talk about is full fine-tuning. So if you've heard fine-tuning described by someone, they've probably said something like it's continuing to train a pre-trained LLM model on new data. And that's description fits full fine-tuning the best. You load in your entire model, you give your optimizer access to all of the weights in that model, and then you feed it new data. And you do the classic back propagation, forward propagation steps in order to predict and learn from those training examples, and then the weights of the entire model potentially change in response to that. But the Hugging Face PEFT library includes access to a number of different types of parameter efficient fine-tuning, where the number of values that can change is not all of the values in the model. So if you've seen, say if you've hunted down some of these model weights before, you'll know that, maybe they release a 7B model, a 13B model, a 40B model, and a 70B model, and, whatever other bigger versions that they potentially have. But basically, that's the total number of parameters that might be shifting in the training process. So in this case, the model that we're going to be working with is the Llama 2 7B model, essentially 7 billion parameters, subject to change. But you can get some of these, I just said there's a 70B model, 70 billion parameters. And, that's a pretty big load for any computer to be working with, especially if it's doing complex linear algebra equations like those that are necessary in backpropagation. So the parameter efficient fine-tuning model introduces a number of ways to train stuff, not necessarily weights in your model, as you'll see, but other stuff that can be attached to it and get out a fine-tuned model, in that it should have improved performance on those metrics that you care about, that take into account what your training data looked like. But in terms of numbers to change around, there should be a lot less of them than the original model that you're working with. So the first is prompt tuning. I don't 100% have a good understanding of this. You load in the model and you freeze all your weights. So what's changing here is not the weights in the model itself. You load in, tokenize, and embed your prompts, and then you create some space in those prompts, aka virtual tokens. So the rest of your prompt is also frozen in place. but those virtual tokens, the optimizer is allowed to change the values of in the course of training. So essentially, it's adding stuff onto your existing prompts in order to bring them more in line with your training data. In order to bring the responses more in line with your training data. LoRA is the one we're going to be talking about most deeply here. It's short for low rank adaptation. Rank of a matrix has to do with sort of the size and shape of that matrix. And like I said, we're doing linear algebra to do these, matrix forward propagation, back propagation steps. So that's where that sort of the matrices are entering into it. But essentially, you attach a set of low-ranked matrices next to particular layers in the network. Specifically, you talk about linear layers in your model, or potentially just the self-attention layers that you can work with. But essentially, the big matrix layer, if you visualize the model weights there as a matrix, one big matrix that is your entire linear layer becomes two smaller low-rank matrices that are trainable. So when the training process goes on, it's the parameters in your low-rank matrices that are subject to change while the original weights are frozen in place. And we'll see a little visualization of this in a second.
Hey, Obi, we've got a question from the chat.
Yes.
So, what is the method you would recommend if you have a small set of data? So this particular person, we only have maybe a few megabytes in the database that they want to pull. So he's trying to understand basically which one of these methods you would use in that scenario.
So this is actually more like something we talked about last week when we talked about your sort of data set construction methods and how that affects your fine tuning. But there is a method that is called transfer learning. That is, you have a small amount of data and you get sort of a small improvement in your model in return. So we talked about how this is something that people use when working with image models to get it used to, treating particular concepts a particular way, like looking for a particular breed of dog when you ask it to generate a dog. But it's not quite the type of thing that you would want for something like question answering or instruction tuning, where you would still want, regardless of which type of fine tuning you're doing, you probably want more examples than that. But in the end, I'd say that the type of parameter efficient fine tuning you use doesn't really matter as much. So I'd say probably LoRA or IA3 here, just because you definitely don't want to do full fine tuning. It's sort of a waste of resources if you have, unless you are doing some like really, really heavy, you have the space for some really heavy workloads, and you also, need a base model that you can use in whatever way you see fit. In this case, I'm not sure whether I can recommend prompt tuning. I don't 100% understand it, where the virtual tokens come from, what they necessarily look like. Is it something that you could just, add on a literal text prefix to your prompts to look at more deeply, or, what is it actually doing with those virtual tokens? But I
So
think that in terms of getting a good adapter that you can, make use of, your methods are mostly going to be LoRA or IA3.
following up on that, is fine-tuning even the right method for this use case? Or would something like
Yeah,
RAG
that's a good
make more
question.
sense?
So depending on what this is something we talked about a little bit last time too, that fine tuning is best when you want to, fine tuning is best when you want to change the sort of attitude of your model. That what you're really changing is how it responds to certain prompts in terms of the like language used or the tactic taken in response to particular prompting. Um, or how it uses certain words, what they mean in particular contexts that maybe don't fully come through in the original like larger data set that sort of trains a general English um, you know understanding.
So to
So
confirm, please.
yeah, so in terms of like ensuring factuality, something like RAG actually turns out to be much more useful in those kinds of contexts.
So a follow-up on that. I was thinking about this. If it sounds like the fine-tuning use case would be great for something like a um, mental health chatbot, where you want to make sure that the way the chatbot is responding is with like kindness and empathy and avoiding trigger words. Is that part of the use case for fine-tuning, something like that?
Yeah, I can see that being potentially useful. I know that a lot of sorry, fine-tuning examples and forays have been for stuff like medical data in terms of, understanding that when you're talking about medicine or health, there are all these words that could theoretically mean other things in other contexts, but in this context, there are special uses that you need to take into account. So for understanding like mental health, not only like attitude in how to speak, because sometimes things like that are better covered by a proper system prompt, depending on
Yeah.
how many resources you have. If you put more effort into building a proper system prompt, you could get out something that treats people kinder, or this associates particular patients with particular attitudes or trigger words, or
Mhm.
so something like that could theoretically even a rag that says this person has PTSD surrounding this topic, please don't bring it up. um you know
System
Things like
prompt very
that.
useful in that case. Yeah.
Yeah.
Much more
So
useful than fine-tuning. Okay. Okay. Thank you.
okay, where was IA3. So IA3 stands for infused adapter by inhibiting and amplifying interactivations. uh Lots of words there. But effectively, just like LoRA adds an adapter to certain parts of your model, IA3 adds adapters to specific parts of your model, specifically self-attention layers, encoder decoder attention layers, and part of the positional feed forward layers. And what it does here, this is something I'm again a little bit shaky on, but the neuron activations, so the outputs of your model, this is something that I haven't actually explained yet. So, okay, neural networks they're made of neurons, which are sort of containers for a value, and those neurons are connected to other neurons by weights. So it's like a graph with edges, and the edges have values that are weights, which determine how individual neurons correspond to other individual neurons further down in the network. Well, some neural networks have sort of backwards facing layers, but mostly it has to do with how neurons at the beginning of the model are related to neurons at the end of the model. But what those values actually are is activations. So the values of the neurons that are modified by the weights are the activations. So in the end of the model, what you're looking at is the activations that determine which word in your sort of token set is most likely and gets predicted as the next word. So basically what IA3 does is it trains these learned vectors. So the one attached to your self-attention layers, the one attached to your encoder decoder layers, and the ones inside your feed forward layers, those are trained by the optimizer. And then those are multiplied. Basically, they act as modifiers on the existing weights. So they scale the neuron activations up or down depending on by what's in the matrix, which is the same thing that the weights do for the previous layer in the network. So the activation of the previous layer goes through the weights and becomes the activation of the new layer, the end layer, and then those activations are modified again by these learned vectors that are sort of the IA3 adapter in those three places. So just looking at some visualizations. So this is what actually led me to understanding prompt tuning a little bit better. But basically, your large language model layers are frozen. Your outputs, your desired outputs are frozen. Your actual prompts, 1 through X, are also frozen. But all of those prompts have extra tokens added to the front that are trainable by your optimizer. So the values of those, so you might visualize the prompts as just words that you're putting in, but what happens to those words is that they become tokens and then they become embeddings. So each word turns into a number, and then those numbers, like more like indices in terms of what a token is. But the embedding is sort of a place on a graph, and depending on what embedding technologies you're using, that can look different. But then it's sort of effectively adding some embeddings to the front, or potentially to the end, or in the middle, however you want to modify these prompts with virtual tokens. Those are being trained. And then this middle one is a representation of LoRA. So you can see the rank here in the middle, at the sort of middle of the trapezoid here. So there's a matrix that's being created, and the reason it's 2 trapezoids is to represent that, it's taking up less space. So your pre-trained weights here are one big block, and every layer is interconnected with every other layer because these are all the linear layers in your model. But they get replaced with trainable, these 2 low rank matrices here. And then eventually they get added back together. But the same way that I described the change in sort of activation at the end for IA3, this is the same sort of thing that's happening here, where your pre-trained weights all stay the same, and then this section here that also acts on the same incoming data can have an effect on what your output looks like. So if all of these matrices here in LoRA are identity matrices, what comes out is the same as what goes in, and it's the same as your pre-trained weights. And then on the right here is your IA3, and this is talking about so these little red squares or purple squares here are your 3 IA3 sort of adapters and where they come in. So at the top here is your feed forward or normalization network. This is sort of an example of the transformer with self-attention sort of model. It's a self-attention block composed of Q, K, and V, and K and V have these IA3 adapters, these learned vectors trained by the model based on your inputs and outputs, that are modifying those particular blocks, K and V. And then also here in the middle of your feed forward normalization layer up at the top, there's another one of these adapters. And that's what's being trained by the optimizer. So obviously the thing that these have in common is that the thing that's being trained by the optimizer is not your model weights, which can be a huge data set so big that it's impossible to load into memory on some machines. All right, and the other thing that makes up QLoRA, so we talked about LoRa adapters, and the other thing that makes up QLoRA is the Q quantization. And I think I actually gave a bit of an incorrect view of quantization last time. I think what I said was that quantization is treating neurons nearby each other as having the same value. That's incorrect. It was sort of inspired by this image here over on the right, where a smaller model still went to all the same adapters. But in this case, that's not what's happening here. So quantization is about sort of the memory representation of your model. So it does make it less complex, which is sort of the thing that I was trying to capture. But it does that by sort of changing the data type of all the numbers in your model. And this is not a one-to-one representation. So we're talking about, in our specific case, 4-bit quantization, which changes the actual numbers that are storing your model weights and activations and changing those from whatever numerical format they were in before, which is usually some sort of float, and then changing that to a 4-bit number. So there are ones where you take your original model weights, which are normally single or double precision floats, or, which also means 32 or 64-bit floating point numbers, and changing those, representing sort of the range of potential weights in your model down in a 4-bit number. And this is kind of, you could see this being an issue where you lose complexity, because what's representable in even a 16-bit floating point number is way off what's representable in a 4-bit floating point number, or a 4-bit int, or whichever data type you end up actually using. So in this case, we're using 4-bit floating point numbers. A 4-bit floating point number is actually the smallest floating point number that you can realistically get, and still, maintain the features of an actual usable data type. So if you know the IEEE floating point format, there is one sign bit for single precision numbers. I think it's one sign bit, 8 exponent bits, and the rest are all mantissa or fractional bits. And the way that works is your sign bit is obvious. Either 0 or 1 corresponds to a positive number, and the other one corresponds to a negative number. And then the exponent bit, you sort of get 2 to the x, but it's sort of shifted, so that, let's say in a 64-bit floating point number, the total number of representable values is 2048 in that exponent section. So it's sort of biased by 1024, so that you can get 2 to the 1024 or to the negative 1024. And then your fractional bits at the end are all determining sort of a fractional scalar that's applicable to that number, or added to that number. So they're all 2 to the minus x, depending on which specific spot you're at. I don't know if I'm explaining this well, but basically your floating point representation has these 3 parts, and depending on how big they are, you get a bigger range of numbers. A 4-bit floating point number is the smallest you can get, and it's composed of 1 sign bit, 2 exponent bits, and 1 fractional bit. So having 1 fractional bit means that the only thing that it can represent is 0 and 2 to the minus 1, also known as 0.5. So the actual range of numbers representable in a 4-bit floating point number is like -4 to 4, just about. It's like -3.5 to 3.5, with a 0-bit, a 0 value, a -0 value, which is usually used as not a number, a negative infinity value, and a positive infinity value, and then -3.5 to 3.5 with divisions of about a half. And that's not, if you're representing model weights, you're going to want more range than that. So what's done is the quantization process takes all of the existing model weights in your in your model, rounds them into these sort of 16 containers, and then associates each representation as a 4-bit floating point number with one of these numbers. So it's not making sure that all your model weights are one of the 16 values of a floating point number. Like, it's not saying you can only have 2, 2.5, and 3. It's saying, okay, these are the 16 values we have for storing numbers, and these are what they correspond to. So it does sort of reduce the complexity of your model in that everything gets rounded towards whatever those buckets are that were created. But it's not actually merging nearby neurons into single neurons.
So Obi, I think that did make sense. Your quantization here is essentially about making sure that are these the new model weights that we're talking about? So the
So
QLoRA layer weights?
everything is being changed into. So this
Mhm.
is something that we'll see a little bit when we look into the actual code. But when you load in the model with these quantization settings to do QLoRA with,
Mhm.
it's already diminished, like cut down in sort of the memory that it takes up. So
Okay.
the Llama 7B model on the file system, as we'll look at later, it's like 14 gigs or something like that. But when we load it in with these quantization settings, it'll be like 6 to 8.
Okay.
So
So could this be configured to use the larger floating point values?
yes, it would take more memory, and it
Yeah.
wouldn't be QLoRA anymore. You'd just be doing regular LoRA.
Great.
Well, there are a lot of sort of half steps, I guess. So when you're using the Hugging Face Transformers library, you can tell it to use FP16, which is a 16-bit floating point format, and that's for speed up. It's technically a form of quantization, but you don't lose as much. Like I said, the 4-bit floating point numbers can only have 16 possible values. Even 16 bits, you can technically quantize to 8 bits as well, if you really wanted to. But I don't think people do that as much.
Okay.
But
Thank you for the
even,
clarification.
yeah. So the normal model, I think, is storing in single precision floats, 32-bit floating point numbers. You can set it to use FP16 for speed up in the Transformers library, or you can set up quantization to turn it into an 8-bit or a 4-bit representation. All right, and the way quantization is set is this bits and bytes config. There are technically a number of ways you can do it. But you can see the things that we're talking about here in terms of parameters for quantization: load in 8-bit, load in 4-bit. So either use int 8 as your sort of representation in memory of these model weights, or use these 4-bit quantization and either use FP4 or NF4 representations. And then there are things about thresholds for outlier detection. So basically, when you're setting your ranges, you don't really want one outlier to make you, stretch the range. So basically, if all of your model weights are inside this smaller range and there's one outlier, you actually want to throw out the outlier to get more closer to the actual values representations of those individual numbers. You can tell it to skip particular modules, so don't quantize this. I think we do this at some point in the code because we still want our output to be converted back into a normal 32-bit number. Things like, does this already have 16-bit weights? Or are we doing this through to a 32-bit or 64-bit float? And then the computational type, what are we doing our computations with. So if your inputs are floating point 32 values, you can tell it to do computation in 16-bit floating point values to get some speed up. Which quantization type are you using? Floating point or NF4? This is use double quantization. So this is, again, sort of about the outliers. So you do your quantization and then you do your quantization again, so that if there are still outliers in that reduced format, you can cut it down to a more representative range. And then it's saying, so most programming languages won't actually mess around with 4-bit data types, because memory in most computers is 8 bits long. Everything is stored in bytes. So it uses packing to fit your 4-bit numbers into some larger data type. In this case, it mostly uses 8-bit integers. uint8 is for unsigned 8-bit integers. But you could theoretically pack them into any larger data type if you really wanted to. And then whatever parameters you can inherit. But basically, it will, in response, it will tell you if the model is quantizable, and it will quantize it for you. And then before we get to the code, the last thing we want to look at is the Hugging Face trainer is specifically made for training transformers. It uses either PyTorch or TensorFlow, Keras, in order to set up the training process. And there are a huge number of parameters that you can set. In this case, the main things that we want to worry about: output directory, checkpointing, setup, stuff like that. But we'll see when we set up the trainer in our code that we're giving it this training argument sort of parameter and specifying what we want to sort of happen with that data. So back to the repo. We went over last week how we use generate training instruction set in our instruction prompts to generate a data set in Astra of instructions, context, results that we want to train the LLM on. And that was generated using GPT-3 and GPT-4. But this time what we want to focus on is this main sort of notebook. So starting at the very beginning, we need to get our model. So this model, Llama 2 7B, the first way that I got this, so if you're using Llama CPP, you can get gguf files, but those aren't loadable into the Hugging Face Transformers format. If you go to Meta directly, what you will get is a PyTorch file, like PTH file for the model weights that is, 12, 13 gigabytes large. But that's also not loadable into Hugging Face Transformers format directly. But the Transformers repo does provide a converter that will convert it. If we look at the format that actually we ended up with, it has our model weights just stored in bin files here. There are 3 of them. They add up to that same, 12, 13 gigabytes of model weights. And then we also take some of the things that were in other directories. So not just the model weights, we're also grabbing the tokenizer and config settings and stuff like that from their original Llama 7B sort of package, the repo that Meta gives you access to specifically. If you can get Hugging Face to accept your Meta application credentials, and it's been accepted, you can actually access, basically, it's not this exactly. I think it's llama 27b_hf on Hugging Face, and you could theoretically access this model with information from with the agreement from Meta and download this format directly. So starting off, we have all our model weights in Google Drive. We copy them over into the Colab environment. We install all our Python packages. We import the stuff we need. And here we set up GPU processing. So it's very simple. If you're using PyTorch, you just say use a CUDA device if it's available. In this case, the V100 attached to the Colab notebook is an NVIDIA device, so it's usable with CUDA. Here we set our quantization settings. Like I said, we're using 4-bit quantization. We're using NF4, doing the double quantization and saying that when you compute stuff, don't use the 32-bit, use the 16-bit for speed up. And then we can use the from pre-train to load in this model config. And then we say load in our model weights. So we give it that same model ID that we set here, and it will go to that folder and get the model weights and load them into memory. And we've already done this again. So you can see model load on CUDA 0, so it loaded onto a CUDA device rather than just our CPU. And then if we look at the memory footprint of this, it is 3.8 gigs, 4 gigs of space, rather than the model weights stored in their files are, 3 times that size, at least. And now that our model is loaded, we can go look at what sort of layers in terms of PyTorch neural network layers it's actually made of. So just like in this picture, for the IA3, we saw Q, K, V, and then, feed forward layers and stuff like that. We can see here Q, K, V, O, a rotary embedding layer, and then up proj, down proj, for feed forward projection layers, post detention normalization, stuff like that. And we can see all of these have size in features 4096, out features 4096. That's sort of the size of the layers. And I think what's going on there is that you have 2048 values and then 2048 position encodings. And that makes your 4096. We'll see in a second. So first we load the model's tokenizer, which is just presented for us. Here we set up our data set. I didn't set up the secrets. Well, while we wait for Astra to give us all our data, let's just continue and come back to this later. So we turn the separated instruction dicts from Astra into a set of combined instructions. So if you've used Llama previously, you'll know that it has special tags for system prompts or instructions. In this case, the tokenizer and the Hugging Face Transformers model handles all that, so we don't actually have to use them. We can just set up our instruction and have that returned to us. Okay, so we load in our data set. You can see there is a lot, but basically it's the same format as we discussed last time. Astra always returns an ID, but it also contains instruction, content, output, and then it has the article ID, which we don't actually use if we wanted to associate it back to the article that this particular prompt was generated from. All right, so now we can turn them into prompts and turn that into a particular data set. You can see this is what the full prompt ends up looking like. And then in the end, it's converted into a single string and put into this dictionary format. Okay, so this is what I was talking about earlier with the 4096 becoming 2048. So we're talking about the max length of the model, and this has to do with what our low rank matrices, what size they actually have to look like, but it's talking about max position embeddings, or sequence length, or end positions, or things like that, that is getting from the model that's telling it that even though these layers are of size 4096, the amount of text that you can actually get into one is 2048 tokens long. And then we need to actually tokenize our data set. In this case, when we did this up here, converted into a single string, we also turned it into a data set from the datasets library. So that means that we can use .map and .filter. And basically, we also use that to shuffle it. So in this case, let's actually change this seed for the shuffle. So that what comes in is in a different. Okay, so this is the section where we freeze all our model parameters. So param.requires grad equals false means none of these layers. So we go through all the parameters in model.parameters and say no backpropagation here, no gradient descent. You are not allowed to train or change these weights at all. And then the small parameters like the layer normalization, they all get cast to floating point 32. So even though we said earlier use FP16 for speed up, there are some things that you don't want in 16-bit, just for stability purposes. And then we enable checkpointing. We don't change any of the number. The number of training sort of cycles before you get a checkpoint. We said require input gradients. And then we have this here, cast output to float, which, turns things back to float 32. And now deciding what is actually going to be, where are we attaching our LoRa adapters to? So if we look again back here, we have QKV. So I think the sort of minimal LoRa that you can do is attach it to Q and V. Or basically some of these in the self-attention layer can get LoRa adapters attached to them, but not all of them have to. But a more effective way to fine-tune your model is to attach LoRa adapters to every linear layer, except for LM head, which has to do with your output here. You can see that it's sort of separated from all of these other list of layers, but it is a linear layer and has the same sort of input features amount. We want to exclude that from having an adapter fitted to it because it turns those 4096 values or 2048 encodings back out into your full text library, basically. So we ask it to tell us which have linear length, so which parts, which layers here are linear, and we get Q, K, up, O, V, gate, down. So all of those ones that were in the self-attention block, Q, K, V, and O, and then also the linear layers from the V4 block here. Okay, so here's the part where we start to see the benefit. We create our PEFT config and then the adapter itself. So LoRa config, 16 attention heads, alpha scaling, et cetera. So these are all setups for training specific LoRa sort of model shapes. So we set up our config, and here's where we start to see, here's where we sort of ask it to do math to tell us what the benefit is. So compared to the trainable parameters in the original model, which are 39, or sorry. So the trainable parameters that we have left now that we've created our LoRa adapter is 39 million. And the total parameters that we were potentially dealing with before is 3.5 billion. So in the end, with our LoRa adapter, we're training about 1% of the total parameters that we would have had to train if we did full fine tuning. So saving ourselves a lot of computational effort here. And then here's where we set up our actual trainer. So like I said, this trainer is optimized for the 4 transformers, the Hugging Face transformers format. The optimizer we're using is Atom 8-bit. We've set our output directory, and then we've set these are specifically for backpropagation. So that's the training arguments that we're actually using. Batch size, accumulation steps, how many steps of forward propagation to understand the gradient, how many warm-up steps do you do before you actually start doing your backpropagation, forward propagation, gradient descent. Max steps is how many data points are we actually going to try. We set this directly instead of defining an epoch size. We just let it break it up into epochs for us.
Sorry for the delay, guys. Obi will be back on momentarily. Sorry, Obi, not getting any audio yet. Technical difficulties. We're doing this live, y'all. Still not, Obi.
How about now?
There we go. Thank you.
Okay. Sorry about that. So I was just talking about sort of max steps in epochs. I think in the end we have 3,800 or something training examples total. And so we could set this to 4,000 and have it run basically fine. There is some danger that if you set max steps to more data than you actually have, then it might start repeating data. And also that otherwise there's no danger of repeating data unless you are using a process that generates data in response to requests, and that has the danger of, depending on how it's built, generating the same over and over again. So we set our learning rate, which is sort of how much are the weights allowed to change each step, whether we're using FP16 for speed up, how many steps do you have to take before you log some outputs, and then where are you putting stuff. And then the data collator gets tokenizer, and it's used to handle feeding the data into the model. We tell it whether or not to use cache. You can enable that to speed up predictions for similar inputs. but we're turning it off here. And then you just call trainer.train. And when we see this, it will talk about how many steps have we done, what is the training loss for this step, and it will have a progress bar at the top telling us how many more steps until we're done. So we said to do 40, and it started doing backpropagation. So training loss is just sort of an internal measure of how far the sort of generated words are from what was expected. And you can see as it's decreasing, that means it's getting more attuned to the training data. It's not necessarily a linear process because that gradient can have local minima or nonlinear behavior, all these sorts of things that, you know, they are the sort of machine learning. They're why machine learning doesn't solve problems, it approximates solutions to problems. If we didn't have to deal with those weird mathematical quirks, we could just get the best output for every problem. So we do this over time. We see the training loss drop. It's probably going to hit a minimum. Well, we only gave it 40 values to work with this time, but otherwise it would sort of, you know, hit a minimum where it'd be able to make minor improvements, but maybe not escape. If it's a local minimum, there's a lot of strategies for using randomness to get your way out of there, and then just going back to whatever the lowest value is that you had stored over time, so that you don't basically waste training cycles in that local minima. You can, at the very least, map out more of the gradient, make yourself more sure of what your minimum is, minimum training loss, than if you just continue to do steps inside that local minima until your training was done. So we did 40 steps, our training loss decreased. And we have stuff stored in outputs. So there was one run here, and we have what we have here is our sort of TensorFlow state. So this does have checkpoints. They trigger every 500 training examples. It stores the model weights. It stores the optimizer state at that time. So you could theoretically grab both of those things and then continue to train from that point if you wanted to.
So, Obi, I have a question. Now that we've
Yeah.
trained this model, we've put this QLoRA adapter onto it, how does it get used? How do we invoke it when we're talking to the LLM?
Yes. So the way that this works is everything you still use the transformers library, but down here you can see, well, this is about saving our model outputs if we're not near any sort of checkpoint. But what happens here is that we say, so let's run this. Come on. Okay. And then we say, let's copy the path, place it here. So our parameter efficient fine tuning model ID is the directory where we saved the model. And then we turn that model ID, so those model weights for the adapter, into a PEFT config. Then we load in our original model here. And then here we turn it into a PEFT model. So our model, auto model for causal LM, this is the base model. Variable called model. That's the base model that we loaded back in. We loaded in the tokenizer because that's what you need to interact with it via text. Then we load in the trained model. So the PEFT model is our combined original model plus adapter. So we can theoretically use this model, original, to get what the original Llama 2 would tell us. And then this trained model here is used with the adapter. So that's the model plus the adapter, and it tells us what the fine-tuned model tells us. So here we find it. Oh, I never actually ran this. That's my bad.
So Obi here is debugging, but essentially you're saying, we define it as a new model and we point towards it instead.
Yes. Sorry, there's something that is. What's our GPU RAM look like? Okay, we run out of GPU RAM. Let's.
It looked like a resource issue, essentially.
Yeah. So let's try this.
And now instead of running on the GCPU, it's just running on the CPU. Looks like there might be a little more to untangle this.
Yeah. Well, I think I might have. Yeah, I can't actually show it running because it doesn't have enough. Okay, everything is reset. Do we still have access to files? Yes. All right, so we have enough space to load in the model, and we can use it just like this. So output tokens equals trained model dot generate batch max new tokens. So the batch is tokenized version of our sort of prompt, and then it gives us back
Yeah, machine learning does take some time.
yeah.
Cool.
Our output.
So let's summarize what the audience has seen here today.
Yes. So after the discussion of fine-tuning types and quantizations, what we've done here in this notebook is take our original model, load it in, quantized, train it on our training set from last time, and then save that, load it back in, and use it to predict on new instruction text that it hasn't seen before.
Thank you. Obi, this is really great. Really appreciate all the time you've put into this. You and I have been working on the third addition to this series. Do you want to
Yes,
speak to
it
that
may
at all?
be another week out rather than happening next week, but the last part of this series is going to be evaluation. So when you have an LLM and you've done fine tuning on it, or say theoretically, even if you've set up, say, a RAG pipeline or something like that, that will give you answers back from an LLM in a way that is modified from what that LLM originally did. Um, how do you determine whether you've seen an improvement? Um, so a lot of the evaluation methods for LLMs are actually very general because LLMs are meant to be generally pretty good at a whole bunch of things.
Hmm.
Um, and so there are a lot of methods that are developed to just do math on the words that are coming out and tell if, does this sentence make sense? Um, you know, a lot of things that are suited for telling you if, say, your fine-tuned LLM, is it better at taking, say, an undergrad code like, you know, computer science 101 test, feed in LLM answers to that and maybe use that to evaluate, or, you know, we fine-tuned this model to do summarization. Is it better at that now than it was before?
Yeah.
And then we'll talk a little bit more about the evaluation method we used in particular, because what we wanted to do was improve its ability to follow instructions regarding text about Cassandra, and determining whether we've done that well is a little bit more of a more involved process.
Yeah. So not next week, but hopefully the following week, we're going to be evaluating how well the fine tuning that we did, um, how well that improved the performance of the LLM. Obi, I just can't thank you enough for this talk. So informative. And for everybody that's listening, please go take a look at the code, get your hands in it. It's public, and you can recreate what was done here. With that, I just want to thank everyone for their attendance, whether you're watching now or in the future. And thank you, Obi. We'll see you next week.
Right? Thanks, Nick.